Dr. Phys, Theoretical Physics, and we come to George Green, the mathematical physicist who did so much. And what's remarkable even more is that he was mostly self taught, didn't go to college until age 40, and a few years beyond that, he got sick and didn't reach the age of 50. So let's look at the Green's function, which is one of the big contributions of George Green. Another is the Green's theorem, which we looked at, the Green's theorem in a plane, which is related to Stokes' theorem. Well, here we're going to look at the Green's function. Well, let's consider a differential equation where we represent it with a big D as an operator, so that this differential operator operates on a function and then it's equal to 0. Let's give an example, the one we did with the low-pass filter. We have here the RC circuit. This is our differential equation. So the differential operator would be R ddt plus 1 over C. When that operates on the charge function on the capacitor, you then get your current, dq dt is your current I, and then Q sits up there and gets your voltage across the capacitor. And then the original differential equation can be adapted to allow for a voltage of input given by some f of t. So we think of it in two steps: the basic generic differential equation without the external interaction, and then the one that adds the external interaction. Well, the idea of the Green's function, as you saw in the last section, is that we want to hit the system, or say smack the system, with the Dirac delta function. That's the impulse. We give it an impulse, and the solution will be the Green's function, which is the impulse response, or the response to the Dirac delta function. So here's our differential equation, a differential equation with the differential operator operating on the x of t, and set that equal here to the Dirac delta function. And here I notice that the x will be the Green's function, and our job is to then do that first, and then when we look at the general solution, you know from the previous section and previous discussions that when we take the Laplace transform, we find the product of the Laplace transform of the f with the g, capital F of s times capital G of s. And when you have the product in the Laplace transform space, it means your solution is a convolution in the regular space. So the Green's function we can write as this g at t minus u, and we're going to define a new notation, capital G, with two arguments. So don't confuse this capital G with a transform, a Laplace transform. That would be, for example, capital G of s. But here I have two arguments, so that should be the clue when we're talking about the Green's function. We have the t, which is a time, and the u, which is a time, and then you do the time shift here on the little g, and that gets you this factor in here, which is the Green's function, or a general form of the Green's function. If you look at u equal to 0, then you have just the g little t, which in our case is the e to the minus t. And then when you shift it, you simply shift it where t gets replaced with t minus u. So the convolution can be written here in this fashion, with the Green's function replacing the little g with the argument t minus u. You go here with the Green's function capital G to replace this, and then intuitively it makes sense to put this factor on the left side where you can see that the u becomes a t. So as we integrate over all the u's, as the Green's function is pulling, you say, the result here to get you your final answer, working on those individual f of u's. So let's just review a couple of things here again. If you should let u equal to 0, then you have the Green's function t comma 0, and that's your basic impulse response to the Dirac delta function hitting you at t equals 0. So that's the secret of understanding the system. And then here we can write the general solution as the Green's function working on the applied voltage function. Now here's a neat way to see what's going on here even at a deeper level, and that is to consider the driving force, or the driving, in this case, voltage to the system, some arbitrary voltage f of t, which we're applying, and we use the f of u because we're going to use the Green's function here to work on it. Each little strip here can be thought of as an impulse, and then the Green's function kicks in. And the Green's function has to be time shifted because you're doing a series of these. If you just do one, like the Dirac delta function, bam, you're done, then you would just simply have the g of t comma 0. And that would be your basic Green's function, the impulse response. But here we're doing more responses, and or more, you're having impulses and responses, going on continuously here. So you think of these strips as some kind of hit to the system, and then the Green's function kicks in and it adjusts to that time. So it's shifted. So if you do it at u, then u sub n, then you would have the Green's function t comma u sub n to work on this one, and then work on this one and work on this one. And the integral is simply summing up all these responses for those impulses given by the arbitrary function.